You're welcome to MTH 202 Plus. In this lecture, we shall consider the rank of matrix and nullity, meant to be a continuation of the previous lecture. In the previous lecture, we considered how to evaluate the rank of a matrix using the number of linearly independent rows. For instance, you may recall that we defined the rank of a matrix in the previous lecture as the maximum number of linearly independent rows the matrix contains. Now, in this lecture, we are going to consider a theorem which will be stated without proof and will prove useful in evaluating the rank of a matrix. Theorem. The theorem is of the fact that the rank of a matrix is invariant under elementary rule operation. Under elementary rule operations. That is the theorem. It's as simple as that. Well, what we mean here is that the rank of a matrix does not change under elementary rule operation. In the sense that the maximum number of linearly independent row vectors of a matrix will not change if the order of row is changed or if a row is multiplied by a non-zero constant or a linear combination of the rows are taken. In other words, we are saying that the rank of a matrix can be determined by reduction to row echelon form. Let's illustrate what we mean by this definition. I'm sure you know what I meant by the elementary row operation, which I know was well taught by Dr. Adirova. Consider the following example. Suppose we are to use the elementary row operation to evaluate the rank of matrix A, given that A is the matrix. A is equal to, of course, the matrix considered earlier in the previous lecture, which is this 1, 2, 3, 3, 2, 1, 2, 4, 6. So how do we use the elementary row operation? Based on the theorem stated above, the elementary row operation will not affect the rank of this matrix. So let's use that. Well, keeping the matrix in mind, I'll write it again here. I have 1, 2, 3. You remember 3, 2, 1. What do you remember again? 2, 4, 6. All right. Remember, in the elementary row operation, we can have a reduced matrix such that the entry here becomes 0, the entry here becomes 0, and the entry here becomes 0. And we may be fortunate or maybe unfortunate, as in some cases, the entry here might be 0, and that would be a very useful information for us. Okay, now for me to have a reduced matrix in which the entry here will be 0, what can I do? What I can do is to have row 2 minus 3 of row 1. When I do that, I have here 1, 2, 3, but here will become 0, and here I have 2 minus 3 times 2. We agree that this will give me minus 4. 1 minus 3 times 3, I have minus 8. And coming here, I have, that's the third row. For the reduced matrix, I want to ensure that the entry here becomes 0. So I'm going to have row 3 minus 2 of row 1. Is that not so? And if I do that, I can be sure that this will give me 2 minus 2, 0, 4, minus 4. I'm going to have 0 and 6 minus 2 times 3, which is 6, so I still have 0. Okay, what do you observe? You observe that the echelon row form that I have here, the reduced matrix, is now this. And you observe that the number of linearly independent rows in this matrix has reduced to 2. Of course, we can be sure that this row here is independent of this row. Of course, a clue to that is the fact that the first component of this row matrix is 0, and of course, the first component of the first row is also 1, non-zero. Okay, so we can be sure that the two vectors are indeed linearly independent vectors. So we have the reduced matrix as 2 linearly independent vectors. Reduced matrix has 2 linearly independent, 2 linearly independent row vectors. What are these row vectors? We have 1, 2, 3, and we have 0, minus 4, minus 8. So what can we say? We see that the maximum number of linearly independent row vectors is 2. Hence, we have the rank of A is what? 2. Yes, so rank of rank A is 2. And you can compare with the previous example that was done in the previous lecture, which we obtained 2, though using another method entirely. Next, we consider theorems that will prove useful later on. We consider 3 theorems which will be helpful in having a sense of what the rank of a matrix is. The first theorem, this time around, I will label the theorem. I will call this theorem 1. theorem 1. Okay, the theorem concerns the fact that you can actually determine whether the row vectors in a matrix are linearly independent or linearly dependent, depending on the rank of the matrix. Okay, for instance, in the above example, you will notice that the number of row vectors are 1, 2, 3. So we have 3 row vectors. But the rank of the matrix is 2. Is that also? Okay. But the fact that the rank of this matrix is 2 provides the information that the 3 row vectors that we have in this matrix are not linearly independent. In fact, we say they are linearly dependent. However, suppose the rank of A is 3, for instance, and noting the fact that we have 3 vectors, then it's a fact that the 3 vectors are linearly independent vectors. All right, so let's now state the theorem in a more general sense. We have, based on this explanation provided, we say that P vectors, well, I'm picking my P to be a natural number. To be more specific, my P is greater than 1. So P vectors with, say, n components, of course, n is a natural number, and I prefer that it is greater than 1. So each are linearly independent, if you observe that the matrix with these p vectors, as row vectors, has rank P, However, they will, but they are linearly dependent if that rank, you can guess what that would be, is less, yes, is less than P. Okay, so we have that P vectors with n components each are linearly independent if the matrix with the vectors as row vectors has rank P, but they are linearly dependent if the rank is less than P. So keep that in mind. Another important theorem relates to the fact that we can have an equivalent definition for the rank of a matrix. And what's that? That you can likewise define the rank of a matrix as the maximum number of linearly independent column vectors of the matrix. also defines the rank of the matrix A. So let's see theorem. I will call this theorem 2, which is also very important theorem, though simple enough, that let R be the rank of matrix A, then the maximum number of linearly independent columns. Linearly independent columns, or say column vector. In that case, we want it column vectors of A is equal to R. Please note this beautiful theorem. Okay, now what can we deduce from this theorem? You observe that in a matrix or in a matrix, the rank, as earlier defined, is the fact that we have the maximum number of linearly independent rows. But this theorem provides an equivalent definition for the rank of matrix A, that it's also the maximum number of linearly independent column vectors. So what can we deduce from this? We observe closely that from this theorem, you see that it is clear that the rank of A will be the same as the rank of the transposition of A. Yes, the rank of A transpose. Okay, that is that. Then we also want to consider another important theorem, which of course I know you will like it. Let's see what that states. Theorem 3. The third theorem in this lecture. Third main theorem. Let me put it that way. So we have P number of vectors. P number of vectors with n components are always linearly dependent, provided n is less than p. Of course, our p and n, what do we mean by them? N, p, they are a natural number with the fact that we can prefer that yes, n comma p, they are greater or equal to 1. Now, keep in mind here that what do we mean? The p number of vectors. For instance, let me give an example here. Suppose you have vector, say 2, 4, vector 1, 3, and vector, say 2, 5. You notice that the number of vectors that are written here is 3. Here, P is 3. But if you look at the component, each vector has how many components? 1, 2, 1, 2, 1, 2. So you observe that the number of components for each of the vector is 2. Now let's go back to the theorem. This is what the theorem is saying, that if P is greater than N, or N is less than P, as we have written it here, then the P vector, the number of vectors will be linearly dependent. That is by default, it will be linearly dependent. So look at it. So what we are saying is that these 3 vectors that we have here, to write them as a set, that this set of vector will be linearly dependent based on theorem 3. Okay, so you keep that in mind. So in this case now, if we form a matrix with this vector, the rank of this matrix will be less or equal to 2, will be less or equal to 2. Okay, now we move on to the next concept, and that is nullity. Nullity of the matrix. Nullity of a matrix. Nullity of the matrix. Well, to get the concept of the nullity of the matrix, you keep in mind homogeneous system, homogeneous linear system, which of course we have considered something related to that during the course of MTH 202's lecture. Linear homogeneous system, of course, can be written as X, we have a vector, and of course, we have 0. Okay? An equation of this form is called a homogeneous linear system. Homogeneous in the sense that you have the right hand side of the equation as you have it here 0, while the unknown is the x vector. Well, in what sense am I writing this? Well, in the sense that if I consider just as written that A is M by N matrix, say of the form A11, A12, and we continue to A1N, A21, A22, up to A2N. Of course, the process is continued. You have AM1, AM2, of course, it goes on and on to AMN. Okay, and we assume that the vector X, well, let's take it as a column vector, which we have X1, X2, which are the unknowns in the homogeneous system, up to Xn. And of course, the 0 there will be n will be with n rows. So we have a system of the form we have the form A11, we have x1 plus A12 x2 plus goes on to A1n xn equals B1. Then we have A21 x1 plus A22 x2. This goes on and on to A2 n x n equals B2. What are we trying to write? We are writing the homogeneous system and knowing the component and the entries of the matrix. And of course, this written as this. Well, you'll notice that in this case now, the right-hand side here, the right-hand side, the B1 is 0. Okay, being a homogeneous system, so this will be 0, and this, of course, will be also 0. And of course, this goes on and on. We have up to the last term here, we have AM1 x1 plus AM2 x2 plus AMN xn is equal to 0. Now, the homogeneous system which has been written down, we consider the solution, okay, of this homogeneous system which has been written this way. Now, what will be the solution? The set of solution of this system actually form a vector space. And this vector space is called null space. Null space. And of course, this you considered in the previous topic for MTH 202. That is the set of solutions of this system, that is this homogeneous system, is called null space. Null space. But what is of interest to us is the dimension of the null space. Also, consider the dimension of the vector space during Dr. Aderogba's class. So, since the null space in itself is a vector space called null space, which of course again is a vector space. It's a vector space in its own right, in the sense that additivity will imply that adding two solutions together will also be a solution of the system, and multiplication by a scalar of the solution will also be a solution. And those are the ingredients that makes the null space a vector space, or a vector subspace, as we will call it. The dimension of this null space is called nullity of A. The dimension of the null space, is called the nullity of A. Dimension, you know what a dimension of a vector space is? Yes, you should remember, just recap the number of linearly linearly independent vector that span the space, okay? And that will give you the dimension of the vector space. So we are saying that the number of linearly independent vector that span the null space is called the nullity of A. Of course, the null space we are dealing with relates to the matrix A, as you can see in the homogeneous linear system. But here is a formula for the nullity. If you really want to evaluate the nullity of A in actual sense, which is the dimension of the null space of A, is equal to the number of columns of A minus the rank of A, minus the rank of A. So